most respected chair of Third International Multi-Topic Conference on Engineering and Science (IMCS), respected keynote speakers, respected organizing team, other scholars, a very good morning. This is Khakoo, a PhD scholar affiliated with Memon University of Engineering and Technology, Jamshoro, Pakistan. I am going to present my work titled on extended Kalman filter for estimation of contact forces at wheel-rail interface in proceedings of Third International Multi-Topic Conference on Engineering and Science (IMCS), which is organized by Faculty of Information Technology, University Yasi, Jakarta, Indonesia. Here are my presentation outlines. As my topic concentrate on the wheel-rail interface of railway system. So first, why study of wheel-rail interface, then introduction, modeling of non-linear wheelset, then designing of extended Kalman filter for estimation non-linear of wheelset model, then simulation results, conclusion, and then acknowledgement and references. So first, why study of wheel-rail interface is being going on, as the wheel track interface is most significant part in railway dynamics, because the forces produced at wheel-rail interface governs or guides the dynamic behavior of entire vehicle. This contact force is complex and highly nonlinear function of creep and affected with other railway vehicle parameters. Therefore, the real knowledge of creep force is necessary for reliable and safe railway vehicle operation. In this presentation, model-based estimation technique is proposed to estimate nonlinear wheelset dynamics. In this work, nonlinear railway wheelset is modeled and estimated using extended Kalman filter algorithm. Both wheelset model and extended Kalman filter are developed and simulated in Simulink, the take of MATLAB software. And now introduction. As already I discussed, the main element of any study of rolling stock behavior is the wheel track interaction page. All the forces which help and direct the railway vehicle transmit via this narrow area of contact, which is wheel track interaction point. Therefore, knowing the nature of these forces is most important for any investigation of general railway vehicle behavior. The wheel track condition information can be detected in real time via real time to provide traction and braking control schemes for re-addition. In the publication of Dr. Imtiaz Hussain, the development of techniques based on Kalman filter proposed for estimation of wheel track interface conditions in real time. However, in this chapter, because this is the suitable for linear systems, so due to nonlinear nature of wheel-rail dynamic behavior, Kalman filter is difficult to use for entire operating conditions. Another model-based technique using uncentered Kalman filter is proposed in this application for estimation of creep forces as well as friction coefficient from behavior of traction motor. However, the estimators in this application seem unreliable in some critical track conditions, and still work is needed to monitor these wheel-rail parameters more effectively in real time. On the basis of fitting nonlinear model, extended Kalman filter can be adapted to identify the wheel track interaction forces and moments that takes into account the interface nonlinearities. Along with this, some detailed literature. I also reviewed the literature. So after reviewing this literature and on condition monitoring of railway wheelset dynamics, it is observed that the problem to analyze wheelset conditions and update them to a desired situation still needs to be improved in order to accomplish the expectation of railway vehicle to be really high speed, high comfort, more safe and economical mean of transport across the world. So it was a little bit introduction and background of my work, and now modeling of nonlinear wheelset. Is the motion of railway vehicle is directed by interaction forces produced at wheel interface. These forces change non-linearly with respect to creepage and are affected by other unpredicted variations in the addition conditions. A single solid axle wheelset shown in figure this one is taken for modeling and estimation of wheel rail conditions. As already we discussed, the in modeling of nonlinear wheelset, creepages are main important. So the creepages, which are actually the relative speed of wheel to a rail of right and left wheels, are expressed here in these equations. As this is the creepage of right wheel and longitudinal direction, and this is the creepage of left wheel and longitudinal direction, and this is the creepage of right and left wheels in lateral direction, because both right wheel and lateral wheel has same lateral creepages. So this is here, and in equation 4 the total creepage of wheels is depicted here like this. So here this omega gamma I means right or left wheel, while j is longitudinal or lateral direction. And other parameter to model the nonlinear wheelset is addition coefficient, that is the ratio of tangential force. Actually here this is the free force to normal force, and hence is also a function of creep. As this figure 2 shows a classic nonlinear change of addition coefficient with respect to creepage for all track conditions. Here track conditions might be dry, wet, poor and worst condition. So following are the equations of creep force and addition coefficient. As here creep force of the right or left wheel is equal to the total force and multiplied by the creepage of particular wheel upon total creepage. Here as mentioned that if I is the total creep force and can be calculated in below equations by Pollard formula. So here this is the total creep force can be calculated, and this is the formula of Pollard which is published in 2005. So here 2 u upon pi k eta upon 1 plus k eta whole square plus r10 k eta. So here n is normal load, and these are the constants. U is actually the friction coefficient, and this eta is the gradient of tangential stress in area of addition, and Ka and Ks are also the tuning parameters. Here friction coefficient is like here this, and eta is 2.3 a square bc upon nu gamma. Here A, B and C are also the tuning parameters, and here this mu is actually the addition coefficient, that is equal to the total force upon normal force. Actually these are the fundamental railway wheelset equations which are also here being used. So here you will see from 10 to 15, these all are the fundamental equations of motion of railway wheelset. Here this is actually the total mass multiplied by the acceleration in forward direction, which is equal to Fxr means force of right wheel in longitudinal direction plus force of left wheel in longitudinal direction, and here this is the mass of wheel multiplied by the lateral acceleration, that is equal to minus Fyr minus Fyr plus Fc. Here Fyr means the force of right wheel in lateral direction, and here this is the yaw rate acceleration, and Rw is inertia, and this is also the fundamental equation, and this is Ts means toroidal torque, that is case theta s plus Cs, like this, and here this is the inertia of left wheel multiplied by angular velocity of left wheel is equal to toroidal torque minus left torque, and here this is the traction motor torque minus toroidal torque minus right wheel torque. As here Fc, like here this one, and Cas we will not use in further designing of extended Kalman filter, because these are very few in quantity, and this Fc is actually being used in curves. So we here are considering the vehicle operating in straight track. So now this is the designing of extended Kalman filter for estimating the nonlinear wheelset model. Being nonlinear nature of railway wheelset model, already we discussed, it is very difficult to estimate the wheelset dynamics with ordinary estimation techniques. Therefore, extended Kalman filter is used to estimate wheelset dynamics and contact forces in all addition conditions like drag, poor, weight, like this. Kalman filter utilizes measurements associated to the state and error covariance matrices to produce a gain known as Kalman gain. Figure 3 is the block diagram of Kalman filter for general scheme. This is actually the block diagram. As extended Kalman filter, which is the extension form of Kalman filter, here we are going to use linearizes the current, mean and covariance by assessing Jacobian matrices and their partial derivatives. From nonlinear model of railway wheelset, a single equation in matrix form is furnished after putting the values of Fxr, Fxl, Fyr, Fyl in equation 11 and 12, that is here you will see 11 and 12. So, and assuming that gamma r means total creepage and of right wheel is equal to the total creepage of left wheel, that is now simply labeled as gamma, and total force of left wheel equal to total force of right wheel is equal to F. So by assuming these things, here this equation is furnished, which is actually now here being used to define extended Kalman filter. So here we are taking 5 variables as the process variables for this extended Kalman filter algorithm, which are actually lateral acceleration, yaw rate, creep or slip, friction coefficient, creep force. These are actually the main 5 variables which are going to be taken for designing the extended Kalman filter to estimate nonlinear wheelset dynamics. And here two quantities are here taken to measure, which are lateral acceleration and yaw rate, which can be measured through accelerometer and gyroscope. So from equation 16, that is actually the metric form, we can furnish or we can derive these further equations with respect to our taken 5 parameters. So this is actually the lateral acceleration and yaw rate equation. This is the total creepage. Here this you will see from equation first or second, I derive from this, taking the values from these those equations, and this is the friction coefficient, and here this is the total creep force. So equation 16 to 17, these are the 17 to 21 here. These are actually the continuous equations which are required to be discretized by using forward Euler method in order to design extended Kalman filter, because extended Kalman filter works in discrete form. As the extended Kalman filter uses a two-step predictor corrector algorithm, so this is the predictor step. These are equations for predictor step. So here this is the process process state, and here this is the error before going to measurement, and this is the equation for corrector step. Here this is the Kalman gain. These are actually H and what we can say H and F. Yes, so these are actually the Jacobian matrices. This is the process state which is going to be updated after the measurement or during measurement, and this is the noise error. These actually are the terminologies which are here given in this table. So it is not a matter of confusion or any doubtness. So this is actually the designing of extended Kalman filter in order to estimate the nonlinear wheelset model's dynamics. And here simulation results. The simulation model of nonlinear wheelset and extended Kalman filter are developed in Simulink and are simulated with 50 microsecond step size. As the vehicle is kept on constant velocity, means no motor torque is applied, only random track disturbance of plus minus 7 millimeter magnitude and lateral direction is applied as input to model for exciting lateral dynamics. Curves of figure 2 are tuned actually with polar parameters Ka, Ks, mu naught, A and B, and this is the table in which we define or derive the values, dry conditions, here the wet conditions, poor conditions, and here the worst condition. So Other than these, the extended Kalman filter tuning parameters are measurement noise covariance of inertial sensors and process noise covariance for entire range of track conditions, which are set in equations 27 to 30. The measurement noise covariance matrix in equation 27 is calculated by adding noise power for accelerometer and gyro sensor, and while the process noise matrices of equations 28 to 30 are calculated on the basis of fine tuning of results. So here these are actually the process noise covariances. Q1 here it is for dry condition, and Q2 is for wet condition, and Q3 is for poor and worst condition. As we have here taken 4 conditions of track, following tests are performed on Wheelset with the extended Kalman filter algorithm. They are dry track condition, wet track condition, poor track condition, worst condition, and last is transition from dry to worst condition. Here in this presentation, we take test number 5, because this is the summary of all 4 above tests. So to save the time, we only here took last test, its results of last test. So this last test is transition test from dry condition to worst condition. Here in result, we calculate lateral velocity and yaw rate of wheelset as well as creep and creep force computed along with errors on all addition conditions which are actually the curve of figure 2, as you will see if these. Yes, this. Therefore, these curves, dry, this is the dry condition curve, this is the wet condition curve, and this is the poor, and this is the worst track condition. So we took these all curves. Here we were on simulation results. Yes. So during simulation, addition condition changed at every 2 seconds from dry to worst addition conditions and first 8 seconds of simulation time, and then condition again changed from worst to wet, because we set 10 seconds simulation time. In first 10 seconds, condition was being changed from dry to wet, then poor, then worst, and after 10 seconds again we change the track condition from worst to wet. The graphs from figure 7 to figure 4 to 7 show the changes of addition conditions and match estimated results with the actual results. Here this is the computation of lateral acceleration. Here both actual and estimated results are very much matching to each other, and here the result error is almost here shown as 0. Similarly, this is the yaw rate computation, this is the actual and estimated yaw rate, and this is the error. Here again error seems 0 with respect to the actual and estimated results. Here this is the creep. Again its error is negligible, and this is the creep force. Here we will see the error at some instants, which are going to analyze in next slide. So in figure 4 to 7 we observed that the extended Kalman filter is a valid estimation technique to estimate wheel dynamics with authenticity. However, estimated Krifos errors in figure 7 become higher for few moments during simulation, as a spike seen at 2 seconds due to sudden change of addition conditions from dry to wet, like here. So here one spike is seen. Overall, extended Kalman filter estimates the wheelset dynamics perfectly for dry, wet, poor and worst addition conditions, and can be used for condition monitoring of rolling stock. This is the conclusion of my whole work. As wheel rail contact force is complex and non-linear function of slip or creepage and affected with other vehicle parameters too. Therefore, it is difficult to estimate wheelset dynamics by simple estimation techniques, and this research extended Kalman filter is used to estimate lateral velocity and yaw rate of railway wheelset as well as creep and creep forces of wheel rail interface. This whole work is validated through simulation MATLAB. Extended Kalman filter estimates not only wheelset dynamics for dry, wet, poor or worst particular addition conditions, but perfectly estimates for transition of all track conditions during simulation. Further, the research is going to estimate the wheel track dynamics and traction and braking modes. Also, work is going on to implement the estimation work on FPGA platform for further commercialization. Acknowledgement. The work is carried out in condition monitoring system lab established at Memon University of Engineering and Technology, Jamshoro, which is part of National Center of Robotics and Automation project of Higher Education Commission of Pakistan. Also, the credit for this research goes to my supervisors. My supervisor is Dr. Imtiaz Professor Dr. Bhawani Shankar Chowdhry and Dr. Tayab Memon for their immense help during the course of this research. Here are the references, latest and concerned, and thank you very much.